Okay, I think this is working this time. So something went wrong with the beginning of the recording. We're looking at will all of this ice melt. It's difficult because we've got two different categories of what could be going on. So unlike our earlier problems in 125 or 128, it's not just a plug and chug. We have to do some logical thinking beforehand. And so the thing we want to compare is the maximum energy the water can lose versus right? We want to compare the total energy needed to melt all of the ice. So we're essentially looking at if my energy got as cold, if my water got as cold as possible, how much energy would it spit out? And then if I put as much energy as possible into the ice, how much energy would that take? So we're trying to figure out, are we in the all ice melts case or ice leftover case? If there's ice left over, we've got to take all the energy out of the water. And if all the ice melts, then this should go to 0. So it's which one is bigger? We do this by looking at the amount, like I find the ice energy one is easier to calculate. I'll just call that Q ice real quick. And that's just going to be an N delta H. We're just looking at the phase change. We can take our 12.13 grams. We can multiply by 1 mole is 18 grams. So multiplying by our molecular weight. And then I have to look up that delta H of fusion for ice, which is 6.010 kilojoules. I'm just going to change it to joules real quick. Right. So doing a quick conversion to joules, because I know this number is going to be in joules. I could have converted this to kilojoules. I just have to make sure my units are consistent. So this will get me how much energy it takes to melt all of the ice. 12.13 divided by 18 times 6010. So it will take 300. Whoa, that doesn't seem. Is that right? I'm not trusting my calculator.
I can double check.
Thank you. Oh yeah, okay, now I gotta do it a third time. That second time was better. I think I missed, I think I did 1.8 instead of 18 the first time.
Okay.
18 times 6010. Okay, that makes more sense. I'm getting 4,050 kilojoules.
That's 6.10?
Yeah, no, 6010, because I switched it, sorry, 4,050 joules.
Okay, yeah, right.
Right, the units of grams cancels out, the units of moles cancels out, and I'm just left with joules. So that's how much energy it would take to melt all of the ice. And now the big question is, does my water have that amount of energy? Does it have more than that amount of energy, or does it have less than that amount of energy? Because it needs at least that much in order to melt all of the ice. So then I check, and I say, okay, well, what's the maximum amount of energy my water can lose? I've got 34 milliliters, which we'll just do the conversion to grams real quick because the density of pure water is 1 gram per milliliter, times the 4.184, the heat capacity for water. And we've got our delta T, our final temperature. If we're losing all of our energy, we're going to the lowest possible temperature of liquid water, which is 0, from our initial temperature of 44.4. And we get a value associated with this. Again, this is in degrees Celsius. We get a value associated with this, and we figure out, is that enough energy to melt all of the ice? 34 times 4.184 times 44.4. Oh. I get 6,316 negative.
Yeah.
Right. So my water could lose 6,316 joules of energy. Again, Celsius cancels, grams cancels. So what this tells me is, oh, my water will melt all of the ice before it gets to 0. And that leftover energy will go to warming the total system. However, if I try to create like a total system from 0 up to some final temperature, there is a way to do that, but I find it's creating an extra process that's not necessary. It does work, right? We can see here that there's like 2,260 joules of energy left over, and we could figure out how much 2,200 joules of energy could warm the total amount of water up from 0. I get confused if I do that. So what I do instead is I say, once I know that we're in this case, right, this. So I'm in this case, hey, grab a chair. I'm recording, by the way. So we're doing this case where the T final is bigger. And there's chairs right there if you want. So I know I'm in that case. Then I can go ahead and do the calculation like we did for lab yesterday. So I'm going to erase what's here right now, and we're going to just do, like once we figure out this is bigger, we know in this case, then we can actually do the math, and then we're just doing a simple solve for like X situation.
I'm not in your class, but I just need help on a lab that I
Great,
have
we can do that in just a moment.
128.
Yeah, great. Have you done the whole melting ice thing?
Yeah, but honestly, I'm confused with this
cool.
class.
So we'll keep talking about it. So after I finish this problem, we'll do more like melting ice problems, because that's again where it starts to get tricky. So we figured out that all of the ice is going to melt, and so we need to figure out a final temperature associated with it. So I'm going to erase my compare stuff. And you can also start paying attention to this part. Is the help you need on the melting ice lab?
It's on the zeroth law lab, if you guys.
The which lab?
I don't know.
The zeroth law lab?
Yeah.
Okay, we don't do that one, but I can still help you with it. Okay, so at this point, we can say, okay, I'm going to have my two different energies. I'm going to have water cooling off, and I'm going to have ice melting and water warming up. So I'm going to end up with a Q1, a Q2, and a Q3. This is going to be my out. This is going to be my in. So I'm going to end up with negative Q1, because I always like to make my out part negative. You don't have to. You can make either one negative. Equal and opposite to my Q2 plus Q3. Then I just plug in my different pieces of information here. I shouldn't have erased that. It's going to be the same number we had before, right? Because it's going to be, no, it's not. It's going to be 34 times 4.184 times T final, the thing that we now have as our question, because we know we're in this yes situation, minus 44. Not forgetting my negative all the way on the outside there, because it's equal and opposite. I've done that in class like every time I've written this down so far.
What is this graph you drew?
So this is like a energy transfer graph. So this is just a way for me to frame my thinking about where the energy is coming from and going to. And it's like I've got a hot system in contact with a cold system. So energy is leaving the hot system and going into the cold system, which I think is kind of like your zeroth law thing.
Yeah, it is.
Right? So my two systems are in contact. This one is going to cool off. This one's going to melt and warm up.
Mm.
And I don't know if you got to phase transitions yet in your class, but we're going to melt and warm up.
We already did.
Okay, cool. So that means over on this side, I have to do the melting, which is the N delta H. I know the N is going to be that 12.13 divided by 18. The delta H, again, I'm going to do the tricky converting to joules ahead of time. That's my Q2. Now I need this amount of water warming up. So that's going to be the 12.13 times 4.184, because melted ice is just water, times my T final, which I still don't know, minus 0, because the melted, when ice melts, it melts at 0. So the starting temperature of this 12 grams of melted ice, which is just water, is 0.
Because the energy is going into the phase change.
Is going into the phase change rather than the temperature change. Now, this does get into kind of some of the problems we have with how we think about it and our world experience of it versus how we interact with it, how we calculate it, right? Because when we melt a piece of ice, the outside melts before the inside. And so that outside water melts away and starts to warm up before the center of it melts.
Wait, are you doing like this equation right here?
Yeah.
Okay.
So what we're looking at here is we're saying, okay, all of the ice is going to essentially melt at the same time before we put energy in. Hey, come on in, come on in. I'm also recording this so it's going to be posted so people can see. And we're just about to finish this problem. So at this point, we're just doing some algebra. Not always that easy, but I'm going to set this up the way I like it. 34 times 4.184 is equal to negative 142.3 times x minus 44 is equal to 12.13 times, divide by 18 times 6010. I better get that same number. I did. 4050 plus 12.13 times 4.184 was 50.8 times t final. I don't even need parentheses because there's a 0 over there. And let's just call it x. Right, and this equation in blue is much easier for most people to approach. Because while this has, I should have included all of my units, I've got this t final, I got these extra parentheses, I've got some units, right? This just looks like a math class, right? If all we were doing was this line in blue, we wouldn't be doing chemistry, right? The fact that this line in blue means something and relates to some physical reality that we had to think about beforehand, that's where this is useful. So, but now we can just do the algebra. I'm going to multiply this through, add this negative x term over. Wait, let's see, how do I want to, oh yeah, and then subtract that one over and figure out what it is. So I'm just going to FOIL and then move things around. So I can go ahead and I can already do plus 142.3 x over here. And I can do 142.3 times 44. I think I dropped a 0.4 in my equation. I'm sorry, but close enough. This is going to be 6261.2 minus 4050. Right, and you can see why I like to have the negative sign on the outside, because then I'm doing addition and I've got a positive number. I get rid of my negatives earlier rather than later. This number is going to come out positive, this number is going to come out positive. I just get positive things. Technically, you could put the negative sign on either side because you can just multiply by negative 1, it doesn't matter. But if I put it on the outside, I get rid of my negatives. I like it. So we do 6261 minus 4050, and we're going to get, eventually this is going to come over here, I'm going to get 2211.2 equal to 193.1 x. Divide by 193.1, and I get x is equal to 11.45. X is my T final. This is going to be in degrees Celsius. And the last thing we can ask is, does that answer make sense? We have two limits on this physical reality. We know it needs to be bigger than 0 and less than 44. Great, we're in that range. Makes sense since there was only like a little bit of energy, and there's only like 2,000 joules of energy left over. It kind of makes sense that's only a little bit warm. Also, if you notice, that thing where I was saying you could do a trick to do this like third process, these two numbers subtracted is the excess energy. These two added together is the total system, right? It's my masses added together times 4.18 versus my energy loss. So there are some shortcuts. I don't want to do too many shortcuts yet because I start to make mistakes and it starts to confuse people. So this is the general approach to will all of the ice melts. First, we have to do a side calculation to figure out whether we're in the yes case or the no case. And then we have to do, since we are in the yes case, we did this system where we were solving for T final. If we're in the no case, we have a slightly different setup where we know T final is 0, but our grams melted becomes the unknown piece. Okay. I'm going to pause this for a moment while we get our next question set up. Oh, first, questions? You all came in the middle of it.
No, I don't even know what you're doing. I'm sorry.
That's okay. Board's erased. Magic. So we're looking at MQ 1.1. I'm going to need you all to remind me what the questions are. I know it's 2, 22, 23, 24, so we're looking at the graded questions. Also, a heads up, I released the graded questions to be reviewed like at the end of the next week. So I'll have it so you can review 1.1. But we got the quiz tonight, so it's also good to do these problems. Let's start with number 2, though, because that's the first problem on the list. Number 2. What does number 2 say?
It says we will allow 71 grams of oxygen to react with 71 grams of ethane. The reaction is shown below. Since the heat of combustion of ethane is negative 1,560.
Ethane C2H. C2H6. Okay.
Negative 1,560 kilojoules per moles. How much heat is exchanged by the system if the reaction is the system?
Too fast.
Oh, sorry.
What was the delta H?
The delta H was negative 1,560.
Kilojoules per mole?
Yeah.
And this is the delta H of reaction?
Yeah.
Okay, so, and we have to be careful about that because one of the first things we have to realize is that, you know, there's the secret unit here that they don't write. It's kilojoules per mole reaction. They assume that since it's per reaction, you already know that. This is a combustion reaction, and we want to figure out how much heat is released by the combustion of how much material?
71 grams of oxygen and 71 grams of ethane.
Okay, so depending on, I have different problems. Sometimes they randomize the numbers. You might have the same numbers. You might have different numbers. The thing here is we've got the same amount of mass, but remember, that doesn't take into account how heavy the molecules are. And we want to know how many oxygens are there to bump into how many ethanes. We also need to balance this chemical reaction. So this is going to go to CO2 plus H2O. This is going to be all gases. Actually, does it tell us whether the H2O is in the gas state or the liquid state at the end?
Yeah, CO2 is in a gas state and the H2O is also in a gas state.
Okay, so we're doing all gases. It could have an effect on the delta H, but we're given the delta H anyway. Great, because the delta H of liquid state is different than the delta H of gas state. We need to balance this. Always double check my balancing, but I think this one's pretty easy. 2, 3. Oh no, this one's a little bit tricky.
Yeah, it's a fraction.
Oh, we could do fractions.
It shows the fraction.
Yeah.
It gives you balance. Oh, that's great. What are the balancing coefficients?
7 halves for oxygen, and then 2 for, and then 3. You're good.
So it's just
That it?
7 halves
Yeah, you're
for
good.
oxygen.
Okay, cool. Right, I was about to double everything to get it so it was 7, 2, 4, 6, but we can do the halves, right? So now what we have to do is we have to figure out what the limiting reactant is. We have to do our 120, our first quarter skills. We have to figure out the limiting reactant and, oh, my calculator's ended up over here. We have to figure out the limiting reactant and calculate how many moles of reaction happens. So we're going to do 71 divided by, so I'll just do it here, 71 grams times 1 over 32 grams. For the molecular weight of oxygen, that's going to get us 2.218 moles of O2. And then C2H6 is going to be 71 grams times, that's 1224 plus 630. 71 divided by 30. Wow, this is almost equal molar. This is going to be equal to 2.37 moles C2H6. So we've got about the same amounts, and I can, depending on how much practice you've done with stoichiometry and identifying limiting reactant, there's a couple different methods. There's moles produced, moles reacted, and by inspection, or guess and check. Guess and check is not a great system to go. You usually end up doing twice as much work to get to the same answer. Moles produced is the way we usually teach it in 124, 127. But moles reaction is actually better in this class because we've already got it in terms of delta H of moles reaction. So I can, by inspection, I can tell this is going to be the limiting reactant. Because right now this is telling me I need about 3 times more oxygen than ethane, but I've got about the same amounts. Right? This recipe of 7 halves O2 with C2H6 tells me if I had this 2.37, I'd want this number to be like 7 or 8 in order to have it be, this limiting. So I know that my oxygen is going to be limiting in this case, but we can also do that through the moles of reaction check. And that's going to be actually really useful this class for this problem because it's already in kilojoules per mole reaction. It's also kind of the easiest way to check, in my opinion. But since most people do the moles produced, I also do that way. The textbook also does moles produced. But what we do is we just take 2.218 moles O2 times
So like 1 mole reaction over.
yeah. I was just blanking out on the units for a second. 1 mole of reaction has 7/2 moles of O2. And we'll compare that to 2.3, I'm going to call it 67. I did a little bit too much rounding there. Doesn't really matter. Shouldn't make an effect in the overall answer, but I want the same number of digits on the two. Moles of C2H6 times 1 mole reaction. So the place where my brain kind of froze for a second there, as I was like, isn't moles reaction supposed to be on the bottom? That's for the delta H, not what we're calculating. Moles of reaction has 1 mole C2H6. So notice, in truth, all we're doing to do this method is we're dividing the compound by its coefficient. We're dividing the compound by its coefficient. So this one, for the C2H6, stays at 2.367. And for the oxygen, 2.218 divided by 7/2, which is 3.5, is 0.6337. Right? And so in this case, the smaller moles of reaction is the limiting reactant. So ta-da, oxygen is the limiting reactant in this case. But since this problem is asking us to find the heat released and we've got this number that's already in kilojoules per mole reaction, we can actually just do 0.6337 times our 1560, and that's going to be the answer as well. If the problem wanted us to continue and calculate the amount of CO2 produced, the amount of H2O produced, there'd be some extra steps, and it would be better if we went back to doing some more calculations. But since it's asking for the delta H, and the delta H is determined by moles reaction, it's just going to be that number. So we can go ahead, and I'll actually show you both the ways we could have done it, right? So what we can do is we can do negative 1560 kilojoules per mole reaction times, and I'm gonna write it out. I'm gonna write this whole step out here, just for fun. The 2.218 moles O2 times the 1 mole reaction for 7/2 moles O2. And the reason I wrote it out like this was to show you kind of how we could have done it 2 different ways, right? So here, I'm converting the moles of O2 to moles of reaction by dividing by 7/2. Or I could have turned my, this looks like a 6. I could have turned my 1560 into kilojoules per mole of O2 by dividing by 7/2 on this side. But since it's multiply, 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 I'm doing the 1 over 7/2 here, or I'm doing the 1 over 7/2 here. It mathematically ends up being the same. So we could have used all of the moles of O2. That O2 looks weird as well. Could have used all of the moles of O2 and changed the delta H, or we can change the moles of O2 into moles of reaction, but it's going to end up being the same number. So pick which way feels better for you. Try it both, think about it both ways, and just pick the one that works better for you. And then we'll get a number that's like 1560 times 0.631, 1560, don't forget the negative, negative 1560 times 0.6337, and we get negative 988.5 kilojoules of energy. So this is a huge exothermic reaction. Negative 988.5 kilojoules of energy released. I had to double check. When I got 988, I was like, wait, is this in joules or kilojoules? Because that's a big number. It's a lot of energy released from burning it. Is that the right answer?
Yeah, it's
Okay, cool.
989.
Oh yeah, I rounded, a little bit of rounding. So, balanced our chemical reaction, did our stoichiometry skills we have from 124. Then had to do our thinking of what's the limiting reactant, lots of different ways to do that. Kind of introducing this idea of moles of reaction to figure out the limiting reactant, which is my favorite. Again, my favorite way, because I just divide by coefficient. I can almost do it in my head most of the time. Often when I'm doing what I call by inspection, where I'm not writing anything down, I'm looking at it, it's because I'm calculating the moles of reaction in my head. And I can just tell. Close enough, right? But in this problem, once we have the moles of reaction, that actually is what we're going to be using for the actual answer as well. Questions on this one, or should we go to number 22? Good. Cool. So let's jump all the way to number 22. Give me a second to erase the board, and then we will look at number 22 together. Again, number 22 is one of the graded problems. I'm fine doing the graded problems even before it's due. So if you want to come in, like if you wanted to ask about 1.2 graded problems, we could do that. But we got the quiz tonight, so we probably want to focus on 1.1. I do need someone to, now because it is a grade problem, you all will have different randomized numbers. So who's got number 22 up to look at?
I have mine.
Yeah, let's do it.
We dropped 90 grams of metal at 67 degrees Celsius into 52 grams of water at 22 degrees Celsius.
Okay.
And the final temperature is 33.5 degrees Celsius.
I already know what's going to ask, but tell me what the question is.
What's the specific heat capacity?
Right, I could tell from the information that was given what the question was going to be. So this is exactly our calorimetry lab. The first part of the calorimetry lab where we got our unknown metals and we warmed them up, dropped them into water, and we saw the temperature change. You can take my chair if you want to. There's a couple folding chairs as well. But I'm not going to sit down for a while. Take the next one. So we've got some things that make sense to us. We've got a hot system in contact with a cold system. They reach thermal equilibrium, right? Whenever we've got a final temperature where like the temperatures have balanced out. Hot system is cooled off, cold system is warmed up. That means we're fundamentally doing this type of thing. Q in is equal to negative Q out. Right? One thing losing energy, one thing gaining energy. We can calculate the different Q's of them, right? We've got all of the information for the water. So let's go ahead and calculate the Q in. That's going to be equal to the 52 grams of water. Well, let's put units. I'm being too sloppy with my units. With the heat capacity, I have it memorized because I do a lot of these problems this quarter. 4.184 joules grams Celsius. You also see it Kelvin sometimes because the delta T works out. And our delta T is going to be T final of 33.5 degrees Celsius minus our initial temperature of 22 degrees Celsius. Final minus initial. That will get us the amount of energy that is going into the water, leaving the hot metal. Plug that into a calculator. 52 times 4.184. What is that? 11.5 times 11.5. Can I tell you all, sometimes it's nice just to, like, because I use the like simple calculator, sometimes I literally have two calculators next to each other so I don't have to use the parentheses button, because I'm just that lazy with using parentheses buttons. But double check my calculation. I got 2,502. Again, in units of joules, because the grams cancels, degrees Celsius cancels.
Yeah, I got the same thing.
Great, so that is the energy going in. And now we can say that's going to be equal and opposite to the energy coming out of this. So we can then do our Q out is going to be equal to mass of metal, 90 grams, times our CSP, times our delta T, where again, we've got the final and initial, 33.5 minus, oh, not 22, sorry, 67. Didn't give myself enough space.
Q out is negative with that.
Yes. Technically, they're only negative when we set them equal to each other, right? Because this can have energy in and of itself, this can have energy in and of itself, and it's when we're looking at the flow of energy where it's coming from and going to, that's when we really got to think about the negatives. Since I called it Q out, let's just go ahead and toss the negative on there since we know we're going to plug it into this. We don't want to solve for Q out, we want to solve for negative Q out. So we'll throw a negative sign here, and we'll see what we end up with. So we're going to have 33.5 minus 67. Of course, gets us, oh, that's convenient, gets us negative 33.5. I thought I had a typo. Multiply by negative 90. And we're going to, ooh, I forgot my negative sign. What we're going to get is negative Q out. I don't need to write it down. Is equal to 3015 specific heat capacity. Now I can just set my negative Q out equal to my Q in, and I'm going to have 2502 equal to 3015 CSP. Don't carry the negative again, right? That is the negative Q out. So I'm going to do inverse times 2502, and we get a heat capacity for our metal 0.829. With the significant figures is 8298, so it's going to end up rounding to 830. Units of joules, grams, degrees Celsius. And we can ask ourselves, is this a reasonable answer? What are the heat capacities for metals around? And that's kind of weird unless you've spent a bunch of time looking at heat capacities of metals. Hard thing to know, but we know what a big heat capacity is. Water has a big heat capacity. So less than 4 is good. Most of the metals are somewhere between like 0.1 and 1. So this is a reasonable answer. Hey, come on in. There's chairs and a stack back there if you want to grab one. Everyone can scoot in a little bit if they want. We're just going through a couple 1.1 problems. So we can tell, because of our familiarity at least with water, we can tell that this is a reasonable answer. And if we think back to our heat capacity lab, most of the metals were between 0.1 and 1. They were somewhere in that range. Some are a little bit smaller, some are a little bit bigger. If you remember, lithium was way up there. But most of the metals were between 0.1 and 1, so this is a reasonable answer. Questions? Is this good for you too?
It's.
Keep watching.
I don't
It'll
know.
be good.
I don't know.
Should we try number 23?
I had a question about
yeah.
specific figures real quick. Do we have to know them? Because I never learned them in my 124 class because it wasn't really necessary.
So I am also, I don't know if I should record this, but I'm also a little lax with significant figures. There's two things that really bother me with significant figures. Not enough digits or too many digits. Right? As long as you're there, and when I say not enough, when I say not enough or too many, I mean by a lot. too many bothers me a lot more than not enough, if I'm being honest. Because our significant figures are actually communicating how well we made a measurement. So if someone puts, like, if you put like 0.829875, I'm like, how did you measure down to like the microjoules? Like, that would be an insane measurement. Like, we don't have equipment to do that in our lab. So 3 sig figs is based on the glassware, balances, and like thermometers we're using. We're usually 3 or 4 sig figs. If you go to an upper division class where you're using much more, like whatever your major is, if you go to an upper division class where you're using a lot more sensitive material, you'll get to you'll get from like 3 or 4 sig figs to like 5 or 6 sig figs. And then those sig figs start to become a lot more important. Graduate level, if you go to graduate school and you start working in industry, you can get really expensive things that measure like 7 or 8 sig figs. And then you actually do report those things, but those are really expensive instruments. For us, because the glassware we have, the instruments we're using, the thermometers we're using, 3 or 4 sig figs is our typical.
Okay, thank you.
Yeah. Other questions? Did you have a
Just
question?
wanted to ask really quick, do you ever write letters of rec?
Yeah.
Okay. I'm doing the transition to the polymers and coatings blended. and
Oh,
I
nice.
or like officially transitioning, so I need a letter of rec, and I was wondering if
Yeah.
you'd be interested in the rec.
Absolutely. Email me and I'll respond with some questions. Okay. You bet. See ya. Number 23.
Yeah, we could do it.
Again, 23. I think 24 is the tricky one. But let's go ahead and do number 23 as well. What do we have? Who's got number 23 up? Do it in green.
We dropped a 605 gram piece of metal
Okay.
at 74 degrees Celsius with a specific heat capacity of 0.5 into 284 grams of water. At 10 degrees Celsius. And then we have to solve for the final temperature.
Right, so this is actually I almost didn't need to erase everything we just did. This is actually pretty much the same problem we just did, except for we've changed what our unknown is. Right, and you'll notice there's no phase transitions. This is stuff from last week. We're not into the phase transitions and as much with the reactions, except for number 24. Right, so this is really MC delta T equals MC delta T, and we're just changing what our variable is. So I'm going to skip a little bit of the work and some of the thought work, and I'm just going to do MC delta T of metal, metal, metal. Actually, I'm going to go ahead and write this out as T final, T initial. T final minus T initial of the metal is equal to, we'll make that side negative because the metal is the hot system, so it's going to be the one losing energy, is equal to MC, again, I'll write out the delta T, T final minus T initial of the water, water, water. Right, in all of in these problems, there's a couple different things we can solve for. We can solve for the heat capacity of the metal. We could solve for the final temperature of the metal. We could solve for the mass of the metal. We could solve for the initial temperature of the metal, right? This is really a 1, 2, 3, 4, 5, 6. This is like a 6 variable problem. As long as we have 5 of the 6 variables, we can solve for the last thing, right? We need as many variables. We need one less piece of information given than the variables, right? So here, I've got the mass. I've got the initial temperature, I've got the heat capacity, I got the mass, I can look that up, I've got the initial temperature, T final is the only thing I don't know. So out of my 5 variables, out of my 6 variables, I have 5 of them. So if we're thinking about this just in terms of a math class, that's how we math it, right? As long as we're given, if we've got 3 unknowns, 2 of the 3 given, you can solve it. This is 6 variables. Because heat capacity for water is constant, right? This is 6 variables. As long as we have 5 of the 6 things, solve for the missing thing. In number 22, the heat capacity was the unknown thing, the final temperature was given. In number 23, the final temperature is, the heat capacity is given and the final temperature is the unknown. We can still go through the whole thought process of the fact that it's like a hot system and a cold system in contact with each other, reaching thermal equilibrium, but one thing losing energy and another thing gaining energy. After we practice that a little bit, we start to get to the point where we can just jump to like this equation with things plugged in. We have to be careful about that because as we see in number 24, if we try to go too quick, I saw this during the lab yesterday too, if we start to go too quick, we forget that we're introducing extra Q terms. And we're going to be doing that more and more into next week, where there's more Q terms, and we're going to be like, wait, what's the extra Qs? This one, though, pretty much a carbon copy of the last problem. So now we can just start plugging values in and solve. Negative 605. This is not negative mass, it's the negative because it's equal and opposite. Negative mass is not a thing. 0.5. And then we've got, I'm just going to call it x because we're solving an algebra equation. Grab a chair. It's if you tuck your bags underneath the desk and the chairs, there's a little bit more space. Minus the initial temperature of 74 is equal to 284 times 4.184 times x minus 10. And when I write this equation in blue, we've lost all of our chemistry understanding at this point, right? And now we're just doing algebra. I don't usually write things like this because I don't like losing all of my chemistry understanding when I'm doing a problem. But just to illustrate how we can kind of like get away from the chemistry every once in a while. Once we do our chemistry thinking, then we can just get to a point where it looks like algebra. Question?
I was just going to say the heat capacity is, or sorry, the specific heat is 0.7, but I guess it doesn't matter.
No, it's randomized for the different people.
Okay.
So you're going to have, you might have a different mass at different temperatures. Like for the graded problems, everyone gets slightly different randomized numbers within reasonable ranges. Okay, so now we can go ahead and solve. Again, I'm going to go through the math steps the way I like to do them. So I'm going to do 605 times 0.5. That's me negative 302.5. Times x minus 74 is equal to, this is just going to give me 284 times 4.184. Oh, so much bigger. This is insane. 1188.2 x minus 10. So, here's kind of a cool thing. When you do mass times heat capacity, specific heat capacity, you get heat capacity, which is how much energy it takes for a particular object to change temperature. Notice the metal has a heat capacity that's like 4 times smaller than the water. So I'm expecting, no, like 8 times smaller. So it's like 3 and that's like 12. No. Oh, because the masses are different too, that's why. Yeah, so it's like, it's about 4 times smaller. So I'm expecting the water to warm up 4 times less than the metal cools off. So that means if I had to guess before I punch things, I always encourage you to kind of get an intuition of what your answer should be before you start plugging things into calculators, so that if you make a mistake in the calculator, you can kind of be like, oh, that's not what I was expecting. So if I had to do a hunch that's like 60 degrees, I'm going to guess this only gets to like 25-ish. I can't tell that until I get this 4-to-1 ratio thing going, but I think 25 would be like the highest possible temperature. Now we'll go ahead and do the algebra. This is going to be 1188.2x plus 302.5x, because I'm going to have a negative that I add over. And I'm going to have 302.5 times 74 is equal to 22385. The negative goes away. This is going to be 10 times added over plus 11882. Everyone okay with that? Plus 11882. So this is going to give me 34267 equal to 2 plus 302.5. Times 34267. I'd say my guess was pretty good. Was it perfect? No, of course not. Can't do math that hard in my head that fast. But, right, we knew that something around 25 made sense for the differences in the heat capacities for the sizes of those numbers. So, if I got something that was much bigger than 25, either my understanding was wrong or I made a calculational mistake someplace and I'd want to double check it. If I got something much smaller than 25, if I got something above 74, I forgot my negative sign. Right? If putting hot metal into cold water makes the metal heat up or the water cool off, then sign flip someplace, right? If I got a value below 10 or above 74, that's got to be a sign flip. Like if I forgot my negative sign. As you know in class, I've started doing until I start punching things into the calculator, that's usually when I start hitting the calculator, is usually when I'm like, oh, the negative sign. So please keep catching me if I forget the negative sign. Just don't throw something at me, but like intellectually throw something at me, be like, negative sign. Because I've been making that mistake way too much this quarter. Again, pretty similar to the previous problem, but the unknown variable we were solving for shifted. Questions on that one, or should we do the tricky one? 24. So we're going through this list of problems from MQ 1.1, kind of getting ready for the quiz, kind of thinking about what's, just making sure we understand it. Yeah.
Is it possible to ask a question about 1.2 or not?
Yeah, no, absolutely.
Okay.
We can do stuff from 1.2 after we do number 24.
Yeah, of course, yeah.
So we'll add that to the list. Which number from 1.2?
I don't remember. It's like the second one, but I'll look it up.
Yeah, I need help on the second one too.
Oh, yeah.
1.2, number 2?
Yeah.
Heat capacity
Cool.
one?
Yeah.
Let's do number 24, and I'll pause so I can check on how you're doing as well. Good? Okay. Who's got number 24 handy?
It says that we mix 66 milliliters of 1.08 molarity nitric acid with 89 milliliters of 0.326 molarity calcium hydroxide. Both solutions are initially at 20 degrees Celsius. What is the final temperature? And then it gives the balance equation in delta H. Is negative 113 kilojoules per mole.
And that's for 2HNO3 plus calcium hydroxide. Whoa, I put my 2 inside the parentheses. That's awkward. Going to 2H2O plus calcium nitrate. Aqueous, 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 liquid. Okay, so this is the delta H of the reaction. If you notice, it's double the delta H of neutralization we calculated in class the other day, but we'll worry about that in a moment. Just like interesting little tidbit. So, in our thinking here, I did this thinking with somebody yesterday, and they thought it was really interesting. So, keeping in mind that when we have solutions like this, it's mostly water, right? How much, so the way we can think about it is, if I figure out how many moles of calcium hydroxide I have, I've got 0.326 times 89 divided by 1,000 times the molecular weight No, I'm doing something special. So I'm just doing like a little thought experiment real quick. Plus 17. So that's 2 grams. So if I'm doing this right, I didn't look it up, but from the numbers I remember from yesterday, this amount of calcium hydroxide, if it was like a solid chunk of calcium hydroxide before it dissolved, would take up only 1 milliliter of space. The other 88 milliliters, all water. Right? So when we look at this, so if we took the moles of calcium hydroxide, found out how much it weighs, and used its density to say if it was a solid chunk of calcium hydroxide, what volume would it be? It's a fraction of this overall volume, right? It's 1/89th, it's 1/88th of this volume. In that situation, we say, look, the other 88 milliliters, all water, right? All water. So when I look at these solutions, these aqueous solutions are really mostly water, to the point where their heat capacities are approximately the same as water, their densities are approximately the same as water. They're really mostly water. So when we look at a problem like this, we're like, let's just treat it like water with a little bit of a chemical reaction happening in the corner. And in that thinking, we can again do our hot thing, being the chemical reaction, in contact with a cold thing, the water surrounding it. So it's like the calcium hydroxide and those little bits of calcium hydroxide and nitric acid bumped together. That's making a little hot spot in contact with all of this cold water. And from that thinking, we can say, oh, this is going to be a Q in, Q out problem again. So we're going to set this up just like we did the other ones, where we're going to have a Q in equals Q out, negative. Don't forget the negative. In this situation, the Q out is going to be the delta H of the reaction. So we're going to have a negative N delta H. And that's going to be equal to the water. That's going to be equal to the MC delta T, that temperature change that's going to happen as the energy flows out of the chemical reaction into that huge volume of surrounding water. We have to be careful about a couple things to make sure we do this right. Of course, the negative sign, don't mess that up. We have to make sure that we get the right moles of limiting reactant or moles of reaction. We have to do some conversion so our N's and our delta H's match in their units. We also have to make sure that our Q out units match with our Q in units. We know that heat capacity is going to be in joules, delta H is in kilojoules, so we have to watch out for that as well. And then we have to make sure we get the correct total mass, because it's going to be both solutions poured together. So we can go ahead and start plugging numbers in and see how it goes. We can do 66 plus 89 to get my total volume, plus 66, 155. And that 155 milliliters, we're just going to assume the density is approximately the same as water. That's going to be 155 grams. Our heat capacity, again, is going to be approximately the same. Technically, it should be a little bit higher, but just a little bit. We're going to say it's 4.184. My delta T is going to be T final, the thing that I'm trying to figure out, minus my T initial, which was 20 degrees. I want to put in all of my units. It's going to bother me if I don't. Joules, grams, degrees Celsius, T final minus 20 degrees Celsius. Okay. Then I have to get in my N delta H. So first I have to figure out what my limiting reactant is, or should we just go straight to the moles reaction method? I don't think all of you were here for this, so there's a couple different ways that we can figure out limiting reactant. What most people do in first quarter of chemistry is they do the moles produced method. So you pick like a product, you say how much calcium nitrate was produced, the one that produces less calcium nitrate is the limiting reactant. Totally fine. One of the ways that I like to do it is the moles of reaction method. Works really nicely when we're doing these thermodynamic systems. Then you also have the by inspection method, which is like you can kind of eyeball it and tell which one it is. You can usually do that after a lot of practice. Most of the time when I'm doing my by inspection method, it's actually doing the moles reaction just in my head. Because in this case, it's just divide by 2. So let's go ahead and do that again. I think I recorded that earlier, I can't remember. So we're gonna do a quick little like side note to figure out the limiting reactant. I'm gonna do my 66 divided by 1,000 times 1.08. That will get me my moles of nitric acid. So I'm going to get point, that doesn't seem right. I think I did 100. Yeah. That's better. Okay, 0.0713 moles HNO3. And I can do the same thing.
Wait, why did you multiply by 1,000?
Divided by 1,000 to get my milliliters into liters.
Oh, okay.
Right. I'm going to do the same thing here. 89. Oh, that's 89 divided by 1,000 times 0.326. I just divided again. 89 divided by 1,000 times 0.326. I can already tell which one is limiting. Wait, can I? No, I did it wrong in my head. But I can still already tell which one is limiting. Right, so to get it into the moles of reaction method, I'm going to do an extra multiplication here, where I say one mole of reaction is going to have 2 moles HNO3. And here, I'm going to say 1 mole of reaction is going to have 1 mole calcium hydroxide. And then whichever number is the smaller moles of reaction is my limiting reactant. You'll notice the reason I like this is because it's moles just divided by coefficient. Moles divided by coefficient. So it actually is kind of easy. As long as it's like 2s and 3s, 0.029 moles of reaction. And this one is going to be 0.0713 divided by 2. 0.0356, 357, I'm rounding some, moles reaction. Right, the smaller, that's probably terrible to read on the video, sorry, but what it says is smaller moles of reaction is the limiting reactant. So I can tell from this that my calcium hydroxide is the limiting reactant. The nice part about doing it this way is now, notice, my units here for my limiting reactant match my delta H already. So then I can just take that 0.029, multiply, and that should get me my correct delta H. Right, if the thing that becomes tricky is if the nitric acid was the limiting reactant, we'd have to take that factor of 2 into account, either in the moles here or in the delta H here, but we have to take that factor of 2 into account someplace. Since it turned out the calcium hydroxide with the 1-to-1 ratio was the 1 per reaction was the limiting reactant, I can just plug that in, 0.029 times -113. I'm going to do an extra check. 000. I'm turning it into joules there. I'm doing a quick multiply by 1,000 to make it joules. Now all of my units should match. This is in moles of reaction. And this is in joules per mole reaction. Moles of reaction will cancel out. This will be in joules. Celsius cancels out. Grams cancels out. I divide over. Sorry. Celsius does not cancel out because I solve for T final. It cancels out on this part when I FOIL, but not on this part. Joules will cancel out when I divide over. Grams cancels out. This will get me in the right units. Question?
Are you supposed to put in units on?
Yeah, I am. Thank you. Right. If we did this math without carrying the negative N delta H, would have messed things up. Now, the nice thing is, you can see why I like to do it on the exothermic side, because it's a negative and negative. I'm just going to end up with positive numbers everywhere. It'll make the math, it'll make punching into my calculator a little less tricky for me. So now we can just do in the algebra. Oh, let's see here. 0.029 times 113,000 is 327 divided by 155 divided by 4.184 plus 20. I got T final 25 degrees, well, 25.1 degrees Celsius. Makes sense for some of the examples we've seen previously, right? When we did this in class, we poured acid and base together. It only went up by like 2 or 3 degrees, right? Even though these reactions are very exothermic, we're only reacting small amounts of material. And that small amount of material is going into a lot of water. So we don't see huge temperature increases in these cases. I'm going to pause this for a moment. Is it still recording? Oh, good, it's still recording. Okay, so we are going, oh, I just went away. Okay, there it goes. So we're going to go ahead and we're going to look at 1.2, number 2. Yeah, please tell me, what is the problem?
You mix 32 milliliters of 1.3 molar nitric acid with 89 milliliters of 0.5.
Well, hold on.
Oh, sorry.
89 milliliters of
0.5 molar potassium
hydroxide.
Hydroxide, yeah. By how much does the temperature increase? Assume the heat of neutralization is negative 57.3 kJ moles. Molar, yeah, moles. And enter your answer in 3 steep values.
Okay, so we want to get a delta T. This is kind of like the problem we just did. It's worded differently. The unknown thing we're solving for has shifted. So rather than just T final, right, we're just saying what's the delta T. There's a couple other assumptions we have to make. Again, mostly water, so we're going to assume that it's a water solution. Chemical reaction is going to be like in a tiny corner in my mind. It's not actually in a tiny corner. It's randomly bumping around everywhere. But in my mind, I always, whenever I'm doing thermodynamic problems, I like to make hot block in contact with cold block. And energy flows from the hot thing to the cold thing. That's just how I do thermodynamics in my head. So the reaction is going to be exothermic, so that's going to be my hot block. The water surrounding it is going to be the cold block, and the energy is going to be released into the water surrounding. So I'm expecting the delta T to be positive, not negative, because I should warm up, not cool off. In terms of the setup, we're going to have temperature change because it's asking us to solve for delta T. So that gives me an obvious that it's MC delta T. And then it also gives me the delta H of reaction. So that's either a trig or this is equal to N delta H. Since this side's exothermic and these are in thermal contact with each other, we'll do negative N delta H. So it's like Q in is equal to negative Q out. Looks like oot, but you know what I mean. Now we're kind of back to that math. After we've done that kind of chemical thinking, thermodynamic thinking, one thing gaining energy, one thing losing energy, we've got an N delta H. We've got to do the limiting reactant thing again, but it's a 1-to-1 ratio, so it's pretty easy. I can start plugging things in. 32 plus 89 is 91 plus 30, that's a 121. Heat capacity for water is 4.184. And delta T is the thing I'm solving for, not T final, T initial, it's just delta T. My limiting reactant, I'm just going to do this real quick. 89 times 0.5 is 44 versus 32 times 1.3, that's 41. So the nitric acid is my limiting reactant. I'm going to have negative, oh, I didn't divide by 1,000, that's why it's so big. Divided by 1,000, it's going to be 0.0 416 moles HNO3 times 57.3 kilojoules per mole reaction. And a couple things I need to be careful about. Again, I got sloppy with my units and I was about to make a mistake. 121 grams, 4.184 joules, grams, degrees Celsius. Notice there's a couple things we got to watch out for. Don't forget the negative sign. My biggest mistake. Joules versus kilojoules. Moles reaction versus moles HNO3. So there's three things we got to be careful about. Now, in this case, the moles reaction versus moles HNO3 is not a big deal because it's 1 mole HNO3 per 1 reaction. Sorry, per 1 mole reaction. So the mole ratio is 1. So it's not going to change my numbers, but it does change my units. This is good to keep track of that. I'm also going to go ahead. We've got two different options. With what a mess I've made over on my right-hand side, I'm just going to do 1 kilojoule is 1,000 joules. So I'm going to convert this side to kilojoules rather than that side to joules just because that side of the board's full. Normally I'm converting kilojoules to joules because I can multiply by 1,000 easier than I can divide by 1,000, but same. So now we do our math. We do 0.0416 times 57.3 divided by 121 divided by 4.184 times 1,000. I calculate delta T equals 4.71 degrees Celsius. And that should make sense because that's again in the ballpark we've seen for all of these neutralizations. We're always seeing it be like 1 to 5, 7, 8 degrees. The only way we can get these acid-base reactions to have a really big increase in temperature is if we do much, much higher concentrations. Right, so there's a lot more reaction happening in a smaller volume. So essentially what we have to do is we have to make our cold block smaller and our hot block bigger. Which we can't do just by adding more stuff, because as we add more solution, we're adding more water as we add more reaction, so both blocks are getting bigger. We have to make the concentration higher. So we're adding more reaction without adding more water. We don't see that very often in this class.
I think what tricked me was just that the negative 57.3, I thought it was temperature, or it was a temperature change. So,
Oh yeah, so we have to be careful about the delta H versus the delta T and how we're thinking about the different pieces of what's going on.
Okay, thank you.
You bet.